Proposition 7. In this proposition, what Euclid demonstrates is that if you have a line segment AB and you draw two lines on the extremities of AB. So in this case, he draws AC and he draws BC and it intersects at point C. He says if you draw on the same side of the line segment, in this case on the upper side, you could have done that same thing on the lower side. If you draw the same line segments in terms of length, so AC you drew as AD and BC you drew as BD, they will always intersect at the same point. Proposition essentially means the same. He does it by contradiction again. So this actually doesn't require construction, but we'll do it with reasoning as well as construction. So suppose you have the line segment AB, and you draw from the extremities, you draw the first point C, and that is where the next line from B meets. So I'm just drawing it roughly. So B meets there. He says, if you take the same length, which is AC, I'm not measuring it right now. When I do it the second time, in terms of construction, we will measure it. And you take the same length BC and you draw it here. They are not same here, but just assume. We'll try to prove it to logic. D. He says this point D and this point C actually are the same if it's on the same side. So here it is on the upper side. So for this case, what we do is we just join CD to reason out. Now what is the reasoning? Let's look at the reasoning. So we know AC is equal to AD. So we know AC is equal to AD. We also know BC is equal to BD. So you see, they're two isosceles triangles. So what happens is this angle, this green angle, is equal to this green angle. So this angle, which is CDA, is much larger than BCD. Okay. This angle is much larger to this angle, isn't it? But we also know in this blue isosceles, this angle and this angle is same, which is contradictory. So essentially he does that. So in terms of definitions, he says, since AC is equal to AD, AC is equal to AD, angle ACD is also equal to angle ADC. Angle ACD is equal to angle ADC. That's the red isosceles triangle. Therefore, angle ADC is greater than angle DCB. Let's look at it. ADC is greater than DCB. This is what we were explaining, the black ones. Then he says, therefore, angle CDB, this angle in the blue isosceles triangle is much greater than angle DCB. We reasoned that out already. And then he says, also, since CB is equal to DB, these two angles should be the same. Therefore, these are contradictory, and which is impossible. So essentially, this point D has to shift towards point C. Now let's try and construct this and see how will it function. So let's take any line segment and then assume this is the first point. We got it here. So I'm drawing it roughly. So you have A, B, C. Now we'll actually measure it with a compass. So what we'll do is we'll take point A, now you see point C, the length AC will always lie on this arc, right? Now length BC. Just measuring BC here. Now we have length BC will always lie on this arc. It's not very accurate, I've done it. Yes, assume it's that. So you see that all ACs will lie on this arc and all BCs will lie on this arc, and they will only meet at this point. There's no other point in which they meet. So this is on this side. The same thing can be done on this side where the two arcs will meet. Okay, so that's the proof of proposition 7, proof by contradiction. You can actually do construction also.